Alrighty, welcome back to operating systems. What happened today? Start of midterms, all right, cool. Or people thought today was Thanksgiving? Week early, but yeah, midterms are a thing. I guess people take midterm week. So today, speaking of midterms, we can go over a question you may not see. So take a rewind back for a little bit, back to scheduling, so we can explore actually doing a type of question with priorities. So one type of priority system you might use is something called dynamic priority scheduling, might also be called feedback scheduling. Basically, this is where we let the algorithm manage priorities in order to avoid starvation, right? We have it if some low priority process hasn't executed for a very long time, we might give it a higher priority such that it will eventually execute. So we let this algorithm manage the priorities, we set time slices, and in this scenario, we measure CPU usage to figure out how long each process has actually executed for. Idea here is we increase the priority of processes that don't use their time slice and decrease the priority of processes that actually use their time slice. So for this, we have to pick a number to mean high priority or low priority. In this scenario, we will pick a lower number, means higher priority, just to make the math a bit easier. So each process gets assigned some priority when it started. Let's call it P of n. And then how the scheduling algorithm works is it just picks the lowest priority number to schedule. If it yields or gives up the CPU, we pick the next lowest number. If there's a tie, we break it with the rival order. And if a lower priority number becomes ready, so a process with a higher priority or lower number than what's currently running, we'll immediately context switch to it and prefer to run it instead. And here, again, we record how much time each process executes for in this time slice called a priority interval if you want. So we'll keep track of how long they all execute for each process, call it C. Timer interrupts still occur, so we do have control in the kernel. We can kick processes out whenever we want. So at the end of our interval or time slice, whenever we update the priorities according to this formula, so they just kind of decay. So the priority of process n is equal to P of n divided by 2. So it gets a bit lower each time since we're dividing by 2, which would mean it's a higher priority. And then we add however long it ran for. So the longer it runs, the higher number, the lower priority, so we would prefer to execute some other task. And whenever we recalculate these priorities, the C is just keeping track of how long they execute for. We reset them back to 0. So what that looks like is assume we have processes with an initial priority of 0, so they are all tied. The processes are X, Y, A, and B, and we'll differentiate two different kinds of processes. So A and B are CPU-bound processes. That means whenever you schedule them to run, they will just execute on the CPU as much time as you will let them. While X and Y are I/O-bound processes, what that means is they'll spend most of their time blocked waiting for information. You can think of it as like being in a read system call or something like that. So in order to kind of emulate I/O-bound processes, we'll say X and Y are I/O-bound processes, and whenever we schedule them, they will execute for one time unit, and then let's assume they take the one time unit to start a system call, and then they block for 5 time units. So they cannot execute anymore. They're waiting for data from a file or a network or something like that. So they can't execute. They're in that block state, and we can actually schedule something else to run. So we assume timer interrupts occur every 1 second. Time slice or priority interval is 10, so we recalculate the priorities of all the processes every 10 time units. So what is the scheduling? So if we get processes X Y, A, and B, they all have a priority of 0, and they all arrive at time 0 in this order. What do we schedule first? Yeah, X, right? It arrived first, same priorities. It's just straight up round robin, first come, first serve. So we'd schedule X, and now since X is one of those special IO bound processes, it executes for 1 time unit, and then it blocks for 5. So 1, 2, 3, 4, 5. So it won't be able to run again until this time right here at 6. So now, if we can't run X anymore, and these are the arrival order and they all have the same priority, what do we run next? Yeah, Y, right? We just run Y. So scheduling, not too bad if it appears on a midterm, right? So we run Y, it executes for 1 time unit, and then it sleeps. It gets blocked for 5. So now at this point, what do I have to execute? A, right? So I can't execute X, it's blocked. Can't execute Y, it's blocked. So I have to execute A. So in this scenario, I would actually execute A for all of the time units, all of the remaining time units until I recalculate my priorities. Why? Well, even though X is ready here at time 6, doesn't matter because it has the exact same priority of process A. Since A is already running, it just won't kick it out because, well, it's already running, same priority, it won't get precedence over it or anything like that. Then at time 7, Y is ready, but again, we wouldn't switch to Y immediately. So at time 10, we have to recalculate all the priorities. So since they all started with 0, it's just 0 divided by 2, so it's just 0. And then we add how long they ran for. So process X ran for 1 time unit, process Y ran for 1 time unit, so there's that number, and then process A ran for 8 time units. So its new priority is 8, and then the priority of process B, it ran for 0, so its new priority is 0. So now at time 10, what process has the highest priority? Yeah, B, right? Lowest number, higher priority. So what we would do, and it has a way, way higher priority or lower number than the rest of them. So for the next 10 time units, we just execute B. And now whenever we would recalculate, right, process X would be like a half, process Y would be a half, process A would be 4, and then process B's priority would now be 10. It got its big fair share. All right, any questions about that? Yeah?
So when we were doing the and we were doing blocking signals, like wait, does the CPU give let the other processes run while it's waiting for that process to end?
Yeah, yeah. So like in your lab, when you did a wait system call, or in the examples, your process would be blocked, it can't run, and the OS would just schedule another process to run, and then make progress, and yeah, just wait for it to be done. Yep.
So in this example, if you said the order was A, X, Y, B, would A run for 10, then X and Y for 1 each, and then B for 8?
Yeah, so if A came first, it would just run for all 10, because they are all tied, and then we'd recalculate, and then yeah, X, Y, and B would all be the same, and then it'd be the same X, Y, and then B. Yeah. All right. Well, we can change numbers too. We can just change it around and say A and B have priority of 6. The others have a priority of 0, so we'd prefer to run X and Y. So if we just take the exact same question again, well, now at time 0, what are we going to schedule to run? So X has a priority of 0, Y has a priority of 0, the number. A has a priority of 6, B has a priority of 6. So we'd schedule X. I see X signs, yes. So we'd schedule X to run. Then, like before, X is blocked for 5 time units. Schedule Y to run, right? And then A, right? A is the next thing. We got a YMCA group. So next thing, here we schedule A to run, but now it only runs for 4 time units because at time 6, X is ready, right? So since X is ready at time 6, and it has a lower priority or lower number, higher priority than A, it immediately kicks it out. So it would kick out kick out A, and then run for its 1 time unit, and then it would get blocked. Now, Y would be ready at this point. It has a lower number, higher priority than A, so we would prefer to run it. It runs for 1 time unit, and then it's blocked for the next 5. So for these additional 2 time units until we recalculate again, we'll just switch back to process A. Now, here, whenever we recalculate the priorities, well, we just put the numbers in. X and Y started with 0. 0 divided by anything is 0. And they both ran for 2 time units. So X and Y's new priority is 2. Process A, well, its old priority was 6. So 6 divided by 2 is 3. And it ran for 6 time units. So its new priority is 9. Process B, it had an initial priority of 6. 6 divided by 2 is 3. It ran for 0, so its new priority is going to be 3. Now, at time 10, what am I going to schedule to run? X? Incorrect. B, right? So X is still blocked. I can only execute X again at 1, 2, 3, 4, 5. So I have to wait 2 more time units so X is blocked, Y is blocked. I have a choice between A and B. B has a lower number, higher priority, so I'd run B for 2 time units. And then at time 12, X is ready again. It has a lower number, higher priority, so it would run for 1. Then Y runs for 1 when it's ready, and then it just switches back to B. Then eventually X is ready, and then eventually Y is ready, and then we're done. So everyone good with that? Lots of fun? All right, let's go to the magic part. Oh, yeah?
When do we recalculate the priorities? Like just right after the process has like gone out of the processing? Like
Just every 10 no matter what, in this case.
everyone?
Every 10 time units in this case, just no matter what. We just the operating system would recalculate it every 10.
Okay.
Yeah. Yeah.
How's the time size different from the priority interval?
It's just like a weird, it doesn't really matter. It's like a weird implementation detail. If you implement it with a round robin or something like that, typically they're going to be exactly the same thing. It's not going to matter because it'll just make the same decision whenever your time slice is up anyways and it needs to reschedule you. So yeah, literally doesn't matter. But just priority interval time slice, you can assume for this they mean the same thing. And we just recalculate the priorities every 10 time units. All right, so next, let's detour back to virtual memory and I will show you some magic. So yeah, LLMs, cool thing, right? So if you have like a 30 billion parameter LLM model and you try and run it, right, this C++ implementation, very efficient. So efficient that people figured like, how is this magic happening? So if I go here, oops, can I click on you? Yeah, so if I go here, they had this model. This model before was like, did they even say? Oh, yeah, so the model itself is close to 30 gigs. I think it was like 20 gigs. And before, the model's 20 gigs, they try and use it. How much memory does it use? 20 gigs. It has to load the whole thing into memory. Well, if they took this course and learned about virtual memory, they can do some magic. So, turns out that if you know how to use virtual memory, then you can actually do all the model inference of that 20 gigabyte model using only 6.8 gigs of RAM. And all they did was change one line of code. Whoa. So I will show you. So first, let's take a detour so we can actually control our process's virtual memory. So there is a system call called memory map or mmap, because of course we need to make it shorter. And that's used to map files into a process's virtual address space. Basically what it does is it returns a pointer to you, which is a virtual address. And that through that virtual address, I can actually access a file directory directly. There's no need for any read and write system calls. So how that works is something, let's go over the API quick. So it's a big, kind of complicated function-ish. Takes 6 arguments. The first argument is you can actually pick what virtual address you get back. If you don't care what virtual address you get back is, you can just set it to null, just let the kernel decide for you. And then the second parameter is the length, so that's the number of bytes that should be valid for this memory map. Then the next is protection flags, read, write, execute. They should look somewhat familiar to you. They look like flags in a page table entry, right? And then the next one is flags, so that's mapping flags. So you can say, hey, is this mapping shared? So when I fork, should the other process have the same virtual memory address mapped to the same physical address, which means you could actually do IPC using shared memory instead of through pipes or anything like that. You can make it private so that when you fork, still independent. You can make it anonymous. That means it's not backed by a file anymore, so I can just grab random memory, virtual memory, and use it if I want. And then the next one is a file descriptor. So I can actually set it up so that if I access this virtual address, then it will populate that virtual page with the contents from a file instead of just random memory. So if it's anonymous and it's not backed by a file, it's ignored. Otherwise, you can actually set it up so that it's populated with the contents of a file. Then the last one is offset, so that's where to start, like how many bytes in to start the mapping. Must be a multiple of the page size, or you can just set it to 0. So let's see a quick little example. So everyone remembers like that read-write example where we just read over and over and over and over again until we were done with the file, right? Kind of annoying. So if I have a huge file, I have to just constantly write read, read, read into a buffer over and over and over again. Kind of annoying. The easiest way to do that without doing any read and write system calls is with mmap. So here, like if I was using read or write, I have to first open a file. So let's go meta and let's open this file itself. So I'll open it for read only. Here, I'll just make sure that I get the file descriptor I assume, because, well, this process probably has file descriptor 0, 1, and 2 all open, so the next available number should be a 3. And then here, I just do this fstat system call. All that does is give me information about this file and populates it into this struct. The only thing I really care about is the size of the file, so it populates it in this field st size. So here, I set up an nmap, so I don't care what virtual address I get back. I will map it as many bytes as the length of the file. I'll say it's read only. I'll say it's private, so it should only be available to me. And this process, even though I'm not forking or anything, and then I'll have it populated by the contents of this file descriptor, and then set the offset as 0. So we'll error check. So if mmap fails, it returns map failed, which I believe is just 0. And then after that, after I set up the mapping, I can just close the file descriptor. I don't need the file descriptor anymore, right? We're abiding by our rules of as soon as you don't use a file descriptor, you just close it. Now, to read the file, I don't have to do any read or write system calls whatsoever. All I have to do now is if I just want to print the contents of a file, I can just print every single character. So I can iterate over every single character, just print every single character, and then after you're done with it, just like malloc and free, you should, if you mmap something, you should unmap it, which is like the equivalent of free. So here I unmap it just to be nice and free it. So now if I run this, I just see the contents of the file. I don't have to do any read and write system calls or anything like that. Cool, huh? And how does that work? Well, this magic is brought to you by page tables. So what it essentially does is, say there's a file, say we have a disk floating around here. It's got a file. All right, it's got a file. Let's assume that the file is like 8 kilobytes big. So it uses like a block-sized page of bytes. So we have block 0. And on this block would be like the contents of the file. So let's say like hashtag include blah, blah, blah for this file. So what the mmap call will do is essentially you get a new virtual address. Whoops. So you get a new virtual address, but what it will do is, in this case, it would set up 2 page table entries for you. So whatever virtual address it gave you, it would make sure that it maps to like whatever the lowest number page table entry is. So you'd have 2 page table entries, 1 for each page, right? So initially, whenever you do the mmap system call, it will just set up these page table entries similar to lab 3 and your copy on write behavior. It's lazy, so the mmap system call will just set up the page table entries and not actually grab any memory for you or anything like that. So what it's actually going to do in this case, the trick it uses is it just sets it up. It sets, let's do it here. It sets the valid bit as 0. So if I tried to access this, I would get a page fault, right? So what it's going to do is, if it maps it as 0, the kernel can use all the other, and this gets into implementation detail. You don't need to know it to this level, but you should be able to follow it. So if the valid bit is 0, I can use, the operating system's free to use the other 63 bits for whatever the hell it wants. And what it could do is, if you do this mmap call, it might set it up such that it knows that, hey, if I access this page table entry, well, then this should actually map to file block 0, and this actually should map to file block 1. And that way, in my program, whenever I access like byte 0, what's going to happen is, well, it would use this page table entry on byte 0. It is not valid, so it would generate a page fault, but the kernel is smart and it will go ahead and fix it up. So what it will do to resolve that page fault is it will grab a new page of memory. It will read from disk, read the contents of block 0. So this would be like include whatever the contents of my file is, and then fix up the entry, make it valid, and then make it point to this after reading from the file for you. So after that, it would retry, and then we would read the hashtag, and everything would be good. And now if we read the other 4,095 bytes, it's already on the page. We don't have to read from a file or anything at all, right? We just read, 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 until eventually, if we start using, if we read byte, I don't know, 4,095, if we go to the next page, same thing's going to happen. It's going to grab a new page as soon as we first use it, copy it from disk, copy its contents, whatever it has on it, and then fix it up so that this entry now points to this page, and then set the valid bit 1, da 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 da. But saves you from having to read from a file over and over again. Kind of neat, huh? They didn't tell you to read from a file like that in 105, did they? But this is a lot easier to use than just read. Let the kernel figure it out through the magic of virtual memory. All right, anything you want me to do with this example? If we want to play with anything? What about, so this is read, right? Let's play with stuff. So if it's read, should I be allowed to do this? Oops. No, what's going to happen? Just going to ignore me? Or what's the kernel going to do?
Is it going to tell you you don't have permission to do that?
Don't have permission to do that? Well, let's see. Segmentation fault. We didn't access anything wrong. Well, we kind of did, right? So you can cause seg faults without just accessing, instead of just accessing memory you're not supposed to access, you can also cause seg faults by accessing memory in a way that you're not allowed to. So this, I'm not allowed to write to it, but I tried to. Right, just like the lab, it would have generated a page fault whenever I first tried to access it. Part of that would check the permissions. Oh, well, you're not allowed to write, so seg fault. And if you could use Valgrind if you want, if you were like trying to debug this or something like that. And it will also tell you that, hey, terminating with seg fault, and it even tells you, which you can now kind of read. It says bad permissions for mapped region. Now you know, now you can read that, right? Now you know under the hood what's actually happening. Means I'm not allowed to actually write to that address. Cool, huh? What else we could do? Because, yeah, has anyone ever tried to cause a seg fault by trying to modify a string literal? That's why. So string literals, your compiler will generate random virtual address for them and map them into read-only memory. And because of that, if you try to write to them, you'll seg fault. So that is the reason why you seg fault. You can also set this up in different ways. So if I wanted to, if I want to use this to modify the file, I have to do some other things. I could just, turn the write bit on. So if I turn the write bit on, and then what's this going to do? Yeah.
Is it going to replace it with A's?
Fill the whole file with A's. Well, let's see if I can brick the file. Whoops. Whatever. Doesn't matter. Let's run it again. So, might think I just filled the file full of A's. So VS Code might not load it, so let's just look at it real quick. Not full of A's. So if you can use this to modify the file, but you have to do a few things. So to actually private means that only for this process and only in virtual memory. If I want to have it modify the file as well, I can just use shared so that any writes I have will be reflected in the file. So it turns out, if I do this, I'm closer to filling the file full of A's, but I won't quite do it. So if I run it, that probably shouldn't happen. What'd I do? Private. Okay, that worked. All right, I've gone crazy. This should have, so I think that won't work because when we open the file, we open the file descriptor for read only, not read write. So we should probably do that, although I'm not sure if that's the issue. So open it for read write. So if we open it for read write now, we should hopefully be able to brick our file. So prints the whole contents of the file like before because, well, we printed it before we modified it. But now if we look at the contents of the file, it's full of A's. So didn't have to do as a write system call at all. If I know how to change all the arguments, I can actually use it to write to the file as well. Fun. So why'd we go over that tangent? So how that basically works is, yeah, mmap is lazy, just sets up the page tables, doesn't actually read any data from a file, doesn't actually pull any physical pages or allocate them or anything like that. All it does is create a bunch of invalid page table entries, sets it up, and then figures out what they actually map to so that whenever you actually use it, it stuffs in some other information into the PTE to figure out what it should do whenever you first access this virtual memory address. So the first time you access the page, generates a page fault, and then the kernel would read data from disk into memory. And this is great because this ensures that only the parts of the file you use actually get read, which you can probably see where we're going with this. So back to the question. That 20 gig file, it only uses 6.8 gigs of real memory. So the reason why this works is because when you do model inference, typically it's really sparse. You don't actually use all the parameters of the model to actually do one single inference. So what did they do? Their one-line change is instead of reading the entire model into memory, they just called nmap. And then they deleted a whole bunch of other code because they didn't need any read or write system calls. So not only did they make it easier from learning what nmap was, they just added a line and deleted a whole bunch of code. So that's basically all they did. So if we wanted to, for some reason, we can kind of calculate how much space we need for page tables just as a result of calling mmap for that 20 gig file. So someone on the comment was like, hey, that might be wasteful because you need to store the page tables as opposed to just reading the file. Maybe the page tables themselves take up too much memory and it's kind of wasteful. So you might want to just do some napkin math and figure out how much space is actually being used by the page tables. So if we did some napkin math, so we have 20 gigs of space we want to map, right? Which is the same as 20 times 2, so a gigabyte is 2 to the 30. So that is how much memory we need to actually set up page tables for. If we wanted to figure out how many page tables we need, first step should probably be to figure out, well, how many entries do I need or how many pages do I need to map, right? So I can start off by figuring out how much space I need for page tables by just dividing the total, that 20 gigs, by the size of a page, right? So 4 kilobyte page, I need to figure out how many pages I need to keep track of. So in this case, I would have 20 times 2 to the 18, and I'll just keep it in powers of 2. So I would have to have that many pages. So if I have that many pages to keep track of, how many page table entries do I need across all my L0 tables? Yeah. 2 entries?
Oh, sorry, no.
So this many pages. So I think the number is, oh, that's a big number. Yeah,
Is it 2 to the 27?
2 to the 27? Off by factor of 2 to the 9. It's just that, right? If that's how many pages I need one entry for every page. Trick question. Doesn't matter what. So if I have that many pages, to figure out how much space I need for just the page table mappings that do the final translation of virtual page to physical page, right? I can take that, let's do white, that 2 times 2 to the 18, so that's how many pages, times the size of a page table entry. So I need one entry for each of them. So that's 2 to the 3. We have 8 byte page table entries. That would be 20 times 2 to the 21, which is like something like 40 megabytes. But that's just across all of my L0 page tables, right? So if I need to keep track of 220 or 20 times 2 to the 18 different pages, and I can fit 512 entries per L0. I can figure out how many L0 page tables I need in the best case if they're all full, right? So if I do this math, turns out this number is like 10,240. So that would mean 10,240 full L0 page tables. All right, well, if I have that many full L0 page tables, do I need any other page tables in order to do the entire translation? Yeah.
You need an L1 and an L2?
Yeah, so I probably need some L1s, but assuming this process is running, each process only has one L2, so I don't need a new L2. I'd probably just have to have entries point somewhere. So in this case, if I take that number I got, so 1024 divided by 512, so that's how many entries we can fit per L1. We can figure how many different full L1 page tables we need, and it turns out that number is 20 full L1 page tables. Which kind of makes sense. I don't need a new L3 page table because what would end up happening is I assume my process has an L2 page table, right? It has 512 entries. And then I would take 20 of those entries. So these 20 entries would point to 20 L1 page tables that are full. So they have 512 entries, and they all go to something that also has 512 entries, all full, which kind of makes sense that it's 20 gigs. So if we write out, if we write out our virtual address from before, so we had 12 bits for the offset, 9 bits for the L0 index, 9-bit for the L1 index, and then 9-bit for the L2 index. But if we take the entire range of things we could point at with just a full L1 page table, it would be all of this part of the virtual address here, which is 30 bits, which is a gig. So it makes sense each full L1 page table can actually can handle up to a whole gigabyte worth of mappings. And if we have a 20 gigabyte file, makes sense that we'd have 20 full L1 page tables. Math makes sense. So in this case, if we actually calculated the entire space lost to our whole page tables. 40 megabytes is a good first approximation, but the real answer is, well, I need 1,000 or 10,240 full L1 page tables plus 20 full L1 page tables, giving me a grand total of 1,260 full page tables or pages. And if I was to figure out how much space that wastes, well, that's just times 2 to the 12, like the size of a page. So if I crunch the numbers of that, and I was being really pedantic, we are wasting actually like 40.08 megabytes, not 40. Wasn't it worth it to do all that math and show our knowledge just for a 0.8 and to be technically right? Of course it was. What a silly question to ask. We must be always correct. But yeah, good first approximation, just space used from the L0 page tables. But you should know that that is a lie. Technically, it's a little bit more. So that was a fun adventure. So all the numbers, if you want, it just should make sense. I don't know why I did this to be technically correct. I'm like that. So